Continuing on with our discussion on electric charge and electric field. In this video, let's take a look at a few examples. First, let's have sample problem number 1. Charged particles are placed as shown in the figure. You have charge Q1 at the origin and Q2 lying on the x-axis, distance r from Q1, and you have Q3, distance 3r over 4 from Q1 at an angle theta with respect to the x-axis. Distance r is 0.02 meters and the angle theta is 60 degrees. If Q1 is 1.6 times 10 to the negative 19 coulomb and Q2 is 3.2 times 10 to the negative 19 coulomb and Q3 is negative 3.2 times 10 to the negative 19 coulomb, determine the net electrostatic force experienced by Q1 due to the other charges. So we know R, 0.02 meters, theta, 60 degrees, and the charges Q1, Q2, and Q3. Now, Q1 and Q2 are positive charges, whereas Q3 is negative charge. We are looking for the net electrostatic force experienced by Q1. You have 3 charges. Q1 will interact with the other 2 charges. Each interaction is 1 force. So Q1 will interact with Q2, that's 1 force. And Q1 will interact with Q3, that's another force. So 2 forces all in all will be experienced by Q1 due to the other 2 charges. Q1 is positive, Q2 is positive, 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 repulsion. Similar charges will repel each other, meaning Q1 will be pushed away from Q2. You have force F1, 2. Q1 is positive, Q3 is negative. Positive, negative, opposite charges will attract each other. So attraction, Q1 will be pulled towards Q3. You have force F1, 3. So Q1 will experience F1, 2 and F1, 3. The net force is equal to F1, 2 plus F1, 3. We are looking for the net force. This is a vector equation. We need to use component method to analyze this equation. So let's start with x component. X component of Fnet, Fnet x. X component of F12, F12 is horizontal, negative direction. So minus F12. Then F13 is diagonal. X component, positive direction, adjacent to angle theta. So positive direction plus F13, adjacent to angle theta, so cosine theta. Using Coulomb's law for the magnitude of F12 and F13, we have negative 1 over 4 pi epsilon naught Q1 Q2 over R squared plus 1 over 4 pi epsilon naught Q1 Q2 over 9R squared over 16 cosine theta. Note that distance between Q1 and Q2 is R, so R squared, and distance between Q1 and Q3 is 3R over 4, so square of this, you have 9R squared over 16. We know all the values. We know Q1, Q2, we know R, theta, epsilon naught is a constant that we know the value of. So, kumpleto, we are able to calculate F net X, negative 1.2788345 times 10 to the negative 25 newtons. Doing the same thing for the y component, we have F net y is equal to 0 plus F13 sine theta, which will give us F net y equal to 1.772004987 times 10 to the negative 24 newtons. Knowing the x component and the y component, we are able to determine the magnitude of F net. F net magnitude is equal to square root of F net x squared plus F net y squared, which will give us 1.776613591 times 10 to the negative 24 newtons. Also using the x component and the y component, we'll be able to get the angle of orientation of F net. Tangent theta is equal to opposite over adjacent, F net y over F net x, absolute value to get rid of any negative signs. Getting the inverse tangent, we'll get theta net is equal to 85.87218.968 degrees. F net y is positive. F net x is negative, which means the orientation of angle theta will be above negative x. Magnitude of F net, direction of F net, putting them together, we have F net is equal to 1.777 times 10 to the negative 24 newtons, 85.872 degrees above negative x. And now we have sample problem number 2. The figure shows three particles, Q1, Q2, and Q3. Q1 is 2Q, Q2 is negative 2Q, and Q3 is negative 4Q. Q1 is placed at this location, 30, distance D, from the origin, 30 degrees with respect to the negative x axis or line. Q2 is distance D from the origin, 30 degrees below the positive x line. And Q3 is distance D, 30 degrees above the positive x line. So Q1, Q2, Q3, determine the magnitude of the net electric field at the origin. So we are looking for net electric field. We are looking for E net. Each charge will produce an electric field at the origin, the point that we are looking at. Each charge will produce an electric field in the surrounding space. At the origin, each charge will have an electric field. Q1 is positive. The electric field that it produces is directed away from Q1. So at the origin, electric field E1 is directed away from Q1. Q2 is negative. The electric field produced by a negative charge is directed towards the negative charge. So Q2 will produce an electric field at the origin. The electric field E2 will be directed towards Q2, towards negative charge. The same goes for Q3. Q3 is negative. The electric field that it will produce at the origin will be directed towards Q3, negative charge. You have electric field E3. So E1, E2, E3. At the origin, you have 3 electric fields. The electric fields will add up. E net is summation of the electric field at the location we are looking at. E1 plus E2 plus E3. Again, just like electrostatic force, electric field is a vector quantity. This is a vector equation. We need to use component method to analyze the equation. Starting with the x component, we have x component of E net. We have E net x. X component of E1. E1 is in this direction. X component is positive direction adjacent to 30 degrees. So, positive E1 cosine 30 degrees. E2, the x component of E2 is positive x direction adjacent to 30 degrees. So, plus E2 cosine 30 degrees. On the other hand, E3 is in this direction. X component is positive direction adjacent to 30 degrees. So, plus E3 cosine 30 degrees. Using the equation for electric field magnitude for a single charge, E1 is 1 over 4 pi epsilon naught, Q1 over D squared. Don't forget to put the charge inside an absolute value because we're talking about magnitude of the electric field. E2 is 1 over 4 pi epsilon naught, Q2 over D2 squared. D2 distance of our charge from the origin. And then E3 is 1 over 4 pi epsilon naught, Q3 over D2 squared. Q1 is 2Q. Q2 is negative 2Q inside an absolute value. So we get rid of the negative sign. So we only have 2Q. The same goes for Q3. Q3 is negative 4Q inside an absolute value. So we get rid of the negative sign. We only have 4Q in the equation. Simplifying the equation, we get E net x is equal to 8Q cosine 30 degrees over 4 pi epsilon naught D squared. 8 divided by 4 is 2. So, E net x is equal to 2Q cosine 30 degrees over pi epsilon naught D squared. Doing the same thing for the y component, we have E net y is equal to negative E1 sine 30 degrees minus E2 sine 30 degrees plus E3 sine 30 degrees. Applying the equation for magnitude of electric field for a single charge and simplifying, we see that the y component will cancel out. E net y is equal to 0, which means E net is just equal to E net x, equal to the x component. So, E net is equal to E net x is equal to 2Q cosine 30 degrees over pi epsilon naught D squared. The answer is an equation because the problem does not provide a value for capital Q and for distance D. The only value provided was the angle value, 30 degrees. So our answer for this problem will be an equation. And that's it for now. That's it for our discussion on a few examples. We'll continue our discussion on electric charge and electric field in the next video. In the next video, we take a look at the concept of uniform electric field. So again, that's it for now. Thank you for watching.